Now, when these transformation, such as translation, scaling, rotation, reflection, and shearing, when it apply on two-dimensional plane, it is called 2D transformation. When these transformations are made on two-dimensional plane, it is known as 2D transformation. So the first point that we are going to see how to represent a point first before starting the actual translation rotation. How to represent a point that we are going to see, and what is actually the transformation matrix. Here we require matrices or matrix to represent the transformation. Now a point is represented in dimensions using one row and two column matrix. Using one row and two column matrix. In two-dimensional, it is represented as a one row and two column like this, x and y. X and y means what? X coordinate, x axis, and it is y axis. So x, y, suppose here it is 1, 2, 1, 2, and 3. So how we represent this point? This one 2, 2. 2 on x coordinate, x axis or x coordinate, and 2 on y axis. So this point is represented as x, x, y. Okay. So it is in 2D, and in 3 dimension, it is represented as one row and 3 columns. One row and 3 columns, x, y, and z. 3 axes are there in 3D that we are going to see afterwards in detail the 3-dimensional transformation. Only remember how we represent a point in 2D and 3D. And this kind of representation is known as row matrix like representation. It is known as row matrix representation that we are going to use here, this kind of representation. Another type of representation is there, in that it is represented as 2 rows and 1 column. It is represented as 2 rows and 1 column. In 2D, it is xy. It is xy, means this point 2, 2 is represented like this. X-axis it is 2 and y-axis it is 2. And in 3D, it is represented as x, y, and z. It is represented as x, y, and z, which is known as column matrix like representation. Which is known as column matrix like representation. So in this way, we can represent a point on x and y axis in 2D and 3D. Once again, the first way is to represent row matrix like representation, in which one row, 2 columns are used for 2D x, y, and in 3D, 1 row and 3 columns are used. That is known as row matrix like representation. And another way to represent a point is 2 rows and 1 column. Means in this way, 2 rows x, y, and in 3D x, y, z. That is known as column matrix type representation or like representation. Suppose we want to represent a line. Okay. So here I draw a line like this. So what is it? It is a line from 1 to 1, 1, 1 to 2, 2. It is a line from 1, 1 to 2, 2, A and B. A is 1, 1 and B point is represented as 2, 2. That we require afterwards. Is it clear? Now the next, transformation and matrices. So matrices are used here as a transformation. Now, for transformation purpose, the matrices are used. Why? Because the point, line, these are represented as a matrix. So, for converting or translating, for rotating, for reflection, we require another matrix that is known as transformation matrix. So, as we are using here the transformation matrix, means in the form of matrix we are using it, we can perform different operation on the matrix. Why the matrix is used here? The first case is that we are representing the point as a matrix. We are representing the line as a matrix. We are representing an object as a matrix in 2D. And that's why we require, if we want to rotate it, if we want to reflect it, if we want to scale it, we need another matrix. And that is known as transformation matrix. It is represented as capital letter T in computer graphics. It is represented as capital letter T, and it is known as geometric operator for performing the different transformation. Means for translation we use the matrix, for scaling we use some matrix, and what are the values in that matrices we are going to see one by one. Only remember that to perform these different kind of transformations, we need the transformation matrix. We use the transformation matrix. First reason is that we represent the point, line, object in matrix form, and second one is that we can perform different operation on these matrices. It is possible to perform addition. It is possible to perform subtraction, multiplication. Multiplication is required everywhere. Another, we can calculate the determinant of a matrix. Okay, then we can generate the transpose of matrix and inverse of a matrix. As all these operations are possible with the matrix, we use the matrix form for transformation purpose, and that we known as a transformation matrix, and it is a geometrical object which is represented as a capital letter T, which is represented as a capital letter T. In 2D, it is 2 into 2 matrix. It is 2 into 2 matrix. The first point is that transformation of point. Transformation of point. We consider, let capital X represent a point P. There are two values. One is, 1 minute. Okay, so a point P is represented as capital X and Y. What is X? It is the value on X coordinate and it's a value on Y coordinate. So X and Y, X on X axis and Y on Y axis. X axis and Y axis. It is a point, suppose it is 1. At this position, it is 1. So it is represent like this, it is a point. We are looking for the transformation of a point. Now, along with this, it represents a point P. Next, we require another matrix T. What is it T? It is a transformation matrix. And for 2D transformation, any kind of point, any type of object, we require a 2 into 2 matrix A, B, C, D. A, B, C, D. So we call it as a general 2 into 2 transformation matrix. 2 into 2 transformation matrix. Now we multiply it. Multiplication of this, it generates x multiply with t. So tell me the multiplication points or calculate the multiplication points. We multiply x, y with 2 into 2 A, B, C, D matrix, which is equal to AX. This one multiply with this row, multiply with this column first. So AX plus CY, and another element we got, that is this row again multiply with this column, BX plus DY, which is equal to, we can write it here, X small x star and Y star. So what is this X star and Y star? These are the new points where the original point xy transform. Xy is the new point where the original coordinate xy transform to this new point. So x star is equal to ax plus cy and y star is equal to bx plus dy. So first example that we are going to see, the example number 1, I write here. Or we can call it are the cases, different cases are there. The first, A is equal to first case. 1 minute. So what is the first case we are going to see here? A is equal to D is equal to 1. A is equal to D is equal to 1. Okay. So in this case, A is equal to D is equal to 1 and C is equal to B is equal to 0. A and D both are 1. So what are these? These are diagonal points. Both diagonal points A and D we consider as 1 and C is equal to B is equal to 0. Then the transformation matrix becomes the identity matrix. See how it is? X multiply with T, X, Y and the transformation matrix. So both A and D are 1, 1, both diagonals and 0, 0. So here the transformation matrix becomes the identity matrix. Becomes the identity matrix. So when we multiply it, what happens in this case? So here the result is as it is xy. Result is as it is xy. So new points are same as the original points. New points are same as the original points. No change in the coordinates of the point. When A is equal to D is equal to 1 means diagonal points are 1 and off diagonal points are 0. Then the transformation matrix becomes the identity matrix and that's why no change in the coordinates of P. Now we consider the second case. D is equal to 1. B is equal to C is equal to 0 and some value for A. So I write it here, X multiply with T, X are XY values and the the transformation matrix is A has some value, B is 0, C is 0 and D is equal to 1. D is equal to 1. So when we multiply this XY with this transformation matrix, what is our result? AX plus CY, correct? AX plus cy, it is 0. And second one, bx plus dy. Bx plus dy. So b is 0 and that's why 0, and dy, it is y as it is. So the result is like this, ax and y. Ax and y is equal to x star and y star. See once again, the second case, d is equal to 1, diagonal points or diagonals 1, d is equal to 1, a has some value and b and c of diagonal points are 0. So when we multiply this with the original coordinates x and y, we will get the result ax and y. Ax and y means x star is equal to ax and y star is equal to x star is equal to ax and y star is equal to y. Means what? There is no change in the y coordinate and only change in the x component. Correct? There is no change in the y coordinates, only change in the x coordinates. So now we'll see it with diagram and example. This case, for example, consider x t where x is equal to 1 1 and t is 2 0 0 1. Transformation matrix t is 2 0 0 1 means what? A is equal to 2, b and c is equal to 0 and d is equal to 1. Now perform this multiplication. What result we will get? What result we will get here after performing this multiplication? I draw here the diagram, simple. How it is? X star values, y star. 1 0 2 3 4 5 6. 1 2 3 4 5. What coordinate I have given here? X y 1 1. So that is our x and y. We call it as a point P that we are going to transform with this transformation matrix. So the result after multiplication of 1 1, what is the result? 2 1. What is the result? 2 1. Okay, after multiplication of this, the result is 2 1, which is equal to x star and y star. So the y value remains as it is, only change in the x coordinate. So I draw it here. The result is 2 1. So that is our P star. So this point is transformed from here to here. What happens here? This point P is transformed from here to here in direction x coordinate only. Y remains as it is. Now you can on your own calculate and take any other transformation matrix and you can check what happens, whether it change only x coordinate or y coordinate. Similarly, if we take another example that a is equal to 1, b is equal to c is equal to 0. Means now a is 1, we are going to assign some value for d. Now I take the same example, x t is equal to 1 1 1 0 0 2. Now here a is equal to 1, b c is equal to 0 and d is equal to 2. Now what are the new points here? X here, x remains as it is, correct, and change in only the y coordinate. X remains as it is and change only in the y coordinate. What is 1 2? 1 and 2. So that is our new point. That is our new point. So you can observe it is transformed only in y direction. Why? Because here a is equal to 1 and d has some value and that's why in only y coordinates. And here, as A has some value, it change only x coordinate. That is the second case. Now the next one, that is third case. B is equal to C is equal to 0 means off diagonal points are 0 and we have to assign some value A and D. We have to assign some value A and D. Both have some value. Now I write here standard matrix X, transformation matrix T. X has XY coordinate and T has A has some value. A has some value, correct? B 0, C 0 and D has some value. A 0, B 0, sorry, A has some value, B and C are 0 and D has some value. When we multiply this, what result comes here? Multiply this row with this column, then we will get AX and YD. AX and YD, which is equal to X star and Y star, which is equal to X star and Y star. So what is this scaling indicates? Scaling of both X and Y coordinates of the original position vector P. What is indicate? Scaling of both X and Y coordinates of point P. Okay. Why? Because we have assigned the value to both X, A and D. Now see it with example. X, T, X is equal to 1, 1 and Y, A, B, C, D 0, 0, 3. Means A is equal to 2 and D is equal to 3. Now multiply it and give the result and check the result. I draw here again the line X and Y coordinate. What is the result here? 2 and 3. 2 and 3. So new points X star and Y star are 2 and 3. So original point 1 is here and the new point is here. So it is P, it is P star. So the point is transformed from here to here. The point P is transformed from here to here. Is it clear? Okay. So now see here in these scaling factors A and B, A and D both we have give some value and off diagonal points are 0. It is a point and that's why scaling means enlargement is not possible to see. But if it is any other object than the point, if it is a line, triangle, rectangle, square, etc., the A and D value of A and D shows the enlargement or compression or any kind of scaling. For example, if in this case A is not equal to D, both are different. In this case 2 and 3. If both are equal, not equal, then scaling is not equal. Scaling is not equal. Okay. If A is equal to D, A is equal to D and greater than 1, then it is a pure enlargement. It is a pure enlargement. Means for example, if there is a triangle like this and we perform A is equal to D is greater than 1. If A is equal to D is equal to 2, then what happens? it is increased, enlarged by size 2, exactly size 2. It is a pure enlargement. And third case, if A is equal to D is equal to less than 1, is less than 1, or we say it is in point, greater than 0 and less than 1. If it is greater than 0 and less than 1, then it is a compression. Means, for example, if A is equal to D is equal to 0.5, what happens about with this triangle? It is compressed exactly half. It is compressed exactly half. But these cases we can apply only in the case of objects other than the point. In point, this is not possible to show. Enlargement, compression, not equal scaling, it is possible to show in triangle, rectangle, etc. that we are going to see afterwards. Now see another case, that is case number 4. Okay, where A and D are negative. Consider another case where A and D are negative, off diagonal points are 0. In the previous case, what we have seen? A is equal to 2, D is equal to 3, means both are positive. But now we are going to consider a case where A and D both are negative. So in that case, what happens? So consider B is equal to C is equal to 0 and A is equal to -1. A is equal to -1 and D is equal to +1. Okay. Then X multiply with T, coordinates XY. Now what is the transformation matrix here? A is equal to -1, 0, 0 and 1. So when we multiply this with this one, what is the result here? We get -X and Y. Correct? What result we will get? -X and Y, which is X new points X star and Y star. Now what it shows? X is equal to -X. What it shows? It shows the reflection through Y axis. What it shows? It shows the reflection through Y axis. Now see it with example. I will give one example here. Suppose X T 0.11 and our -1, 0, 0, 1. What is the result here? X equal to -X and Y is equal to Y as it is. So that is our new coordinates X star and Y star. Now I will show it with the simple line. X minus values are there. So I need -1, -2 also in X and Y direction. Now what is our original point? It is 1, 1. That is our point P. What is our original point? 1, 1. That is point P. And what is the new point? -1, -P. Means X is equal to -1 and Y is equal to 1. Okay. X is equal to -1 and Y is equal to 1. So here our point is transformed from here to here. What we call it as a reflection through Y axis. You can see reflection through this Y axis. It is reflected here. It is reflected here. See, once again I am explaining. If A and D, both, any one of these negative, both are negative, then in that case, it shows the reflection through the axis. Here we are going to take one example. A is equal to -1 and D is equal to 1. So when this transformation matrix is multiplied with the original coordinate x and y, it shows -x and y. So the new coordinates x star and y star are -x and y. What it shows? Reflection through y-axis. For example, if we take the original point P11 and the new point, this reflection matrix, then after multiplication it is -1. It is 1, 1. Now it is -1, 1. So it shows the reflection through y-axis. Now we take another example. We'll take another example. X t 0.11 as it is. Instead of a is equal to -1, now here we make d is equal to -1. Here a is equal to -1. Here now d is equal to -1. So what is our result here? -1. It is equal to 1 and -1. It is equal to 1 and -1. So new coordinates are x star is equal to 1 and y star is equal to -1. Okay. What is new here in diagram? X is equal to 1 and y is equal to, it is 1 minus 1. It is 1 minus 1. Means what happens? This point P is reflected here through which axis? Through x-axis. This point is reflected here through our x-axis. So we call it as a reflection through x-axis. What we call it as a reflection through, correct, reflection about x-axis or reflection through x-axis. Now the another case, next case we are going to see here. I think it is case number 5. Case, if again off diagonal points are 0, A is equal to D is less than 0. Both are negative. Means what? Both are negative. Here we consider as example the same 0.11 and both are -1. A is -1, D is -1. Then what is our result? -1, -1. These are the new coordinates x star and y star. Now see it diagrammatically, then it becomes simple to understand. This is x, x star, y, y star. 1, 2, 3, 4. -1, -2, -3. -1, -2. Okay. What is our original point? It is 1, 1. So I draw it here. That is our original point 1, 1. And what is the new point? -1, -1. That is, it is P 1, 1 and it is P star -1, -1. Correct? Means what here? It shows the reflection. This point is transferred from here to here. Transformation, simple translation. So what it shows? It shows the reflection through origin. What it shows? Reflection through origin. It is reflection through origin. So both reflection, scaling and these, whatever the examples or the cases we have seen of coordinate, only diagonal points. Means A and D we considered here. What we consider here? Only A and D considered. That is diagonal points are considered. Diagonal points are considered. Off diagonal points are kept here 0 in all these cases. Now we consider the effects of the off diagonal terms. Means B and C. B and C we kept here 0 in all the cases. But now we are going to consider the effect of off diagonal points. Effects of off diagonal point, that is B and C. So first case that we are going to consider here, X T with A is equal to D is equal to 1 means what? Now we are going to keep the diagonal points both are 1 and C is equal to 0 means we are going to see the effect of B only. X, Y, A is equal to 1, B has some value, C 0 and D is equal to 1 means diagonal points both are 1 now. B has some value and C is equal to 0. What is the result of this multiplication? It is X multiply XY multiply with 1 0. Correct? So X remains only and second XY multiply with B and 1. So it is BX plus Y into 1 Y. It is BX plus 5. See once again, here we consider the diagonal points equal to 1 and off diagonal point effect where B has some value and C is equal to 0. When we multiply it with the original coordinates X and Y, this row multiply with first column and then this row multiply with the second column, we will get this result X BX plus Y is equal to the new coordinates X star and Y star. The new coordinates X star and Y star means what here? What we observe here? That X star is equal to X. It remains as it is. X star is equal to X means X coordinates of the point P unchanged. X coordinates of the point P unchanged. But Y star. What is Y star? It is BX plus Y. BX plus Y. Means what? Y star, the new point on Y coordinate depends linearly on it. Depends linearly on original coordinates. It depends linearly on original coordinates. Both depends on both original coordinates X and Y. It depends linearly on both original coordinates. You can observe here Y star is equal to BX plus Y. Means X and Y both are required here to get the value of Y star. Means the Y coordinates depends linearly on the original coordinates X and Y. This effect is called shearing. What we call it as a? This effect is called shearing. What we call it as a shearing. Remember this word. This effect is called shearing. Here it is proportional to X coordinate. In this case, it is proportional to X coordinate. Now see with example. Suppose 1 and it is 1, B is equal to 2, C is equal to 0. A and D both are 1. Diagonal points are 1. We are considering only B of diagonal, that is B is equal to 2. So I write here B is equal to 2, C is equal to 0. A and D both are equal to 1. What is the result? What is the result here? X star is equal to X. As per our calculation, X star is equal to X. So what is X? As it is. And Y star is equal to BX plus Y. Y star is equal to BX plus Y. What is B? 2. So 2 multiplied with 2 plus 1. The new points are, it is 1, 2 and 5. The new points are 2 and 5. X star is equal to 2 and 5. So that is effect in with example of B. If we consider, instead of B, we consider some value for C. Another case we consider here. A is equal to, D is equal to 1, B is equal to 0 and C has some value. Then this sharing is proportional to the y coordinate. How it is shown, see here, X, T. We take the same example, 1 and B is equal to 0 and C is 2 here. So here B is equal to 0, C is equal to 2, A is equal to, D is equal to 1. What is the result? In this case, it is opposite. When we multiply this, Y star is equal to Y and X star is equal to X plus C1. Correct? What is X star? X plus CY. So the result is y star is equal to y, means y remains as it is, and x is equal to, x star is equal to 4. X star is equal to 4. So that is known as shearing effect. What we call it as a shearing effect, where the diagonal points are kept 1 and off diagonal point has some value. Now the last point or the last case, suppose x, y, the coordinates are 0, 0. Means origin point. We consider the origin point of a line. Means here, suppose this is the x, y star. We consider this point, which is 0, 0. Transformation of this point, whether it is possible. Transformation of this point, whether it is possible. No, it is not possible. Why? Because when we multiply this 0, 0 with any transformation matrix, the result will be 0. The result will be 0. Means the new coordinates x star and y star is equal to 0, 0. Means this point remains here as it is. Not possible to transform the origin. It is not possible to transform the origin. Point 0, 0 we cannot transform. And that is the limitation of point transformation. That is the limitation of point transformation, that we cannot transform the origin. It is a limitation. Now this limitation we can overcome by using homogeneous coordinates. And what is these homogeneous coordinates? We are going to study in detail afterwards. Okay. Only remember that it is not possible to transform the origin point, that is 0, 0. That is the limitation of 2D transformation of a point. But this is also possible with the help of homogeneous coordinates, and that homogeneous coordinates we will see in detail afterwards.